And let's go look at question 3, can't stop bending. So let's take a look at my ceramic cantilever beam. So once I see ceramic, I know that my Young's modulus could be at 300 pascals. I'm going to say my nu is equal to 0.2. So we previously cleared our kernel here, so let's go do the same thing. So my y is equal to 300 times 10 to the 9. We're going to look at nu, which is equal to 0.2. So here we go. All right. Gauge factor is 2.1, so I'm going to say F is equal to 2.1. After the load is applied, the DAC reads 1.2 volts. So I'm going to assume delta V naught is going to be that. So 1.2 volts. String gauges are placed. Okay, so here we go. So the string gauges are placed at approximately a third of the length of the beam away, where the cantilever beam is secured. So a third. So this distance where they're applied, so that's 1/3 of my length of my beam. But I need the distance from where the load is applied. So we'll look at that. The load is applied at the center of the beam. So I'm looking at a third from here, and then this is at a half of the beam. So a half of my length here minus a third. So let's look at that distance. So let's look at half. So what is the length of my beam? Let's see, the length of my beam is 11 meters, so L is equal to 11. So the distance is equal to where the load is applied, so 1/2 L from where basically they are, which is basically a third of the length away. So 1/2 third minus 1/3. Oops, let's go ahead. 1/3 times L. So that distance minus, so it's half and then a third away. Minus 1/3 L. So again, that's going to be our distance there. So if we're starting, essentially this would be just a half and a third. Anyways, so we got that, except I don't want capital, I want little l here. We're also told that length of the beam, the thickness, which is our height, is going to be 20 millimeters, so 20 times 10 to the minus 6. And then we're also, and the width of the beam, so my base is equal to 0.1. And this is where I probably want strain at bending is equal to 6 times P times D divided by E, actually my Y, times, let's go ahead, all the way back into lecture 9. We want to have this equation, that bending equation on our, let's look at our example here. So over here, so my bending 6PD BH squared. So times our base times H squared. There we go. That's our bending. So we've got that. So let's go back to our question. Let's see what else. The width is 0.1 meters. 20, oops, not 10 to the 6, minus 3. And the excitation voltage, so our V sub I is equal to 5 millivolts. 5 so 5 times 10 to the minus 3. Trying to get too ahead of myself. All right. So what assumption must we make in order to solve this problem? So we're assuming that the DAC reads this, and that initially our initial voltage at balance is equal to 0. So that the change in voltage is this. So we need to make sure that we satisfy essentially the relationship that we derived way over here, which is that if we're at balance and we have our two voltage divider circuits, our Wheatstone bridge configuration, standard configuration, we have to satisfy this relationship right here. So that's the assumption that we have to make. So now we need to calculate what's the applied load. So we are definitely going to use this equation, delta V naught I equals F over 4 times epsilon 1 minus epsilon 3 plus epsilon 4. So we know this. We just need to figure out, okay, so what's the strain in the 1? So the strain in the 1 is going to be, when I pull or push, bend it, this is going to be pulling in this direction. So it's going to be compressing. So that's going to be minus nu EB plus ET. And that is going to be the same for my second strain gauge. So I'm going to go ahead and write that down right now. So E1 is equal to minus nu times EB plus ET. E2 equals E1. And then if I look over here, my third strain gauge, E3, is just equal to minus E bending plus ET. and then my fourth is going to be equal to, so now it's being compressed, so that's going to be plus nu EB. So when I look at that, so I'm going to write those values down. 3 is equal to minus EB plus ET, and then E4 equals nu times EB plus ET. There we go. So I'm going to go ahead and just write out that. So F divided by 4, E1 minus E2 minus E3 plus E4. What am I left with? P. So I could go ahead and solve for delta V naught divided by VI, set that equal to this, and solve for P. And that's my load. So that is the applied load in newtons. So P is equal to this. Here we go. So my bending is thus right here. Turns out this ceramic has a linear thermal expansion coefficient of 10 to the minus 5 inverse Kelvin. And this loading occurred when the temperature dropped by 100. What is the new output voltage, assuming the same load is applied? So new output voltage is exactly the same because, again, we're in a full Wheatstone bridge configuration, so that doesn't matter. Trick little question there. All right, now we're on to the last one. Basically a nice little fun problem of an alien monolith in Utah. So, and strain rosettes, of course. So I'll see you all in the next video. Thanks.